All right, I wanted to take a stab at reviewing everything that we covered in this course. So the framework for everything we did in here is the OSI model, these 7 layers, starting at the lowest level with physical connections among devices, and at the highest level going all the way up to applications that talk one to another. At the end of the day, it is about data communications, which is the course title, meaning how do different things communicate back and forth. We covered a lot in each of these areas except for session and presentation, but the others I'll talk about next. So on the physical and data link layer topic, primarily we focused on, in this area of lecture, talked about cabling, twisted pair, some of the issues with these being that as data travels down copper wires, it does have the inherent flaw of being susceptible to interference. And so we do things like twist wires or shield them to try to reduce that amount of interference that happens. We also learned about fiber optic cable and the fact that, generally speaking, this allows us to send more data down cables relative to copper cables. And we built some cables in class, which gave us some better ideas about that. Some of the devices related to our physical cables include repeaters, hubs, bridges, and switches. One of the things we're concerned about are collisions as it relates to the Ethernet technology, collision sense, multiple access, collision detection. The big idea from that is just that if you have a lot of devices connected to the same physical network, too much traffic can result in collisions that will ultimately slow down network throughput as we have to retransmit information in order to get it through. Each of our devices have MAC cards. These have addresses in them which uniquely identify them, which are different than IP addresses. And so initially we just have our unique MAC addresses associated with each device on a local area network, and then we do some work to get an IP address assigned to the device that has a particular MAC address. Here's just an example of what an Ethernet frame looks like. So it's a packet of information that we would send around on a local area network. We don't need to know too much about this other than that we can view it in tools like Wireshark. We also talked about wireless networks, and the big takeaway from this is that as we go to the left end of the spectrum, that the wavelengths are really long and they don't carry as much data, but they can travel really far. And on the other end of the spectrum, we get wavelengths that are really, really short and close together, and they can carry an incredible amount of data, but they don't travel very far and they're subject to disruption. It's important to know that with wireless transmission of data, that there are things that can attenuate or reduce the amount of data being transferred. The signal itself, the strength of the signal, that wavelength, it gets disrupted as we pass through physical objects or bounce off physical objects, for example. And here are some examples of devices, antenna that have unique purposes that help us send and receive data. And of course, the different patterns are related to different cases that you might be involved with. And so there's not just one antenna that's good for every situation. All right, as we move up the OSI stack, even though this is the DoD stack on that picture, we get to the idea of the network itself. And what's the network about? And IP addresses. It's this idea that everything in the world, we need to be able to locate it, and it's sort of analogous to a building. We need to find the address of the building. That would be our network, and then our individual office cubicle, which would be like the specific host number that we're looking for. So over here we have a network 172.18.0.0. It's separated from another network by a router, and within this particular network we have a bunch of IP addresses that all share that same prefix, the 172.18. Among our IP addresses, we have different classes of addresses that represent the first 3 numbers, 1 to 126, 128 to 191, and 192 to 223. Also, we need to be aware of the private address space. Once we get out of the public internet area, we For example, inside of office buildings and stuff, we have our private address schemes that we can assign out. This becomes important as we consider building out our own cloud infrastructures currently, or in the past, just if we have a regular office space. These are all the addresses that we have that we can assign out depending on whether we want to use an A, B, or C address scheme. It doesn't really matter too much, just as long as you select one of them that has enough host addresses for the network you're trying to set up. We also talked about how these numbers relate to octets and binary. We can take any 3 digits and turn them into a binary representation of that with 8 ones and zeros. And using that information along with a subnet mask, which is an uninterrupted string of ones before you get to the zeros, you can determine the network ID that you're on. So remember that routers separate our networks, and so we need to know what part of our address is the network and what part of the address is being used for assigning individual hosts. All right, at the transport layer, we're concerned about whether or not our IP packets actually make it from point A to point B, and we have transport control protocol, which we know means that we're going to ensure that our packets get there because there's going to be some type of check, and then there's going to be user datagram protocol, which means we send something out but we don't know that it's going to get there. And when we're sending things back and forth, we use over a network, we use ports to not only determine where the information, what's the return address for communication that's being sent out, but also what's the destination for where that's supposed to go when it gets to a particular IP address. And we know that that relates to services. Typically we'll have a service running at a particular IP address on some server somewhere, and so we need to tell our IP packets which service they're going to be connected to once they do get to that other device on the other end of the wire. As it relates to TCP, again, keep in mind that port numbers are the endpoints. So again, that's the beginning at the beginning place of the return address as well as the destination. We need a port number there for this to happen correctly. And there's something called a three-way handshake that takes place where we send along numbers back and forth between the sending device and the receiving device. And once there's a synchronization of those numbers going back and forth, then the rest of the communication takes place to send the actual information. But this establishes that you are ready to have a communication between two devices. There are common ports that we use that are good to be familiar with: HTTP, SMTP, and DNS. By the end of the class, obviously you'd use those things a lot, but these are things that we need to be aware of all the time because oftentimes we're poking holes in firewalls, and when the firewalls aren't opened up, that means we're not getting data back and forth that we need. All right, talking about routers. Routers are about passing IP packets back and forth between networks, and in order to have that happen effectively, routers actually keep a table of information related to where they should send their IP packets. So they'll often be connected to one or two other devices, and they need to know which route they should send it through in order for the packet to ultimately get to its destination. So in this particular example, there are actually 3 different networks here, and so if you're sending from A all the way over to, from LAN A to LAN B, these routers here, router A and B, need to understand what they're connected to so that when they receive a packet, they know which of their physical cable ports to send it out to. And when I say port here, I mean a physical one. So if you receive something from A and it's got an address destination that's over there in B, it doesn't look like it's directly connected to that address scheme, and so it's going to pass it off to router B, which does have an awareness of some other network, and it'll pass it on to ultimately the right host. And so there may be many different routers involved with sending something from LAN A to LAN D or LAN A to LAN C. So the routing tables in each of our routers help them communicate one with another and determine the best route to send it through, or the best wire, because you could consider the connections between these to be physical wires. All right, DHCP and host names. So why do we need DHCP? We got a little bit of practice with setting static IP addresses on devices, and that can be a little bit laborious, particularly if you're talking about not just 1, 2, or 3 devices or computers, but what if you had thousands and they're always changing locations or coming on and off the network. So we let software have DHCP running, and it will assign out IP addresses automatically. The overall process for this can be described with the acronym DORA: Discover, Offer, Request, and Acknowledgement. The idea being that a device needing an IP address but having a MAC address, of course, sends out a broadcast which might touch multiple DHCP servers, and DHCP servers respond back and say, hey, would you like this address? And you choose one of them with your request. You respond back to a particular server and say, yes, I'd like that address. And then the server responds and says, okay, you are officially acknowledged as having a particular address that you requested. All right. So if you need to talk between different computers, oftentimes we refer to computers using host names. These are human readable names, such as Win10A, Win10B, or a domain name. So if you're in a local area network, you're going to use human readable short names like 10A and 10B. If you're on the internet at large, you're going to be using domain names. But we need some way of mapping, some system for mapping these human-friendly readable names to IP addresses. And so one thing we can use is particularly with the traditional DNS and not the Windows system, but with just regular DNS, we have a local host name, like what is your computer named? That's one way of knowing how to pass things around. A computer always checks itself first. Like if I'm going to send a packet out, it first checks, am I that particular device? The next thing it'll do is it'll look in a host's text file. That's the original infrastructure architecture of the internet, looking in a text file that's on most machines that associates host names with IP addresses. And if that doesn't work, then go and check your closest DNS server, which is probably located at your internet service provider. There's also some Microsoft-specific tools for more likely if you're trying to find Win10A, 10B in a network and perhaps circumvent the IP addresses and such. Okay, so if you are resolving a domain name, you're going to start off with a particular computer. You're going to go to your internet service provider, and if this is the first time that this website has been looked up, it's going to go to a root name server to find what is the top level domain IP address for the thing you're looking for, like .edu. Having found that, you can now go to the .edu name server, which can look up your domain name that you're looking for, such as BYU, and so the edu top level domain servers will know where the BYU name servers are, and so the next step is it'll go there. So there's a multi-step process before it finds the IP address of the name server that knows of where BYU websites are. So similar for any .com address or something like that. Our DNS system allows us to create records on any DNS server with a variety of different types. A records are important, MX records are important for mail delivery. As you may have learned, debugging DNS issues is very important, and so a couple tools we have for that is you could type in NSLOOKUP and type in the domain that you're looking for, and it will return the IP address that you were searching for. You can also reverse that and say NSLOOKUP and type in an IP address, and it'll tell you what's the domain name associated with that IP address. Other things you can do is you can search for DNS traversal tools on the internet. There are many, such as ultratools.com/tools/DNS traversal. If something's broken in your DNS process, going through tools like this can help you understand where things have fallen apart. Another thing we've talked about are directory services. So what are directory services? So in any given network, particularly a local area network, we need to keep track of the people that are authorized to use devices and services on the network, as well as the devices and the services themselves. And so we use a directory service to keep track of everything that's available electronically in a network. One of the most common ones, directory services we have is Microsoft Active Directory. And there are many different directory services out there in addition to Microsoft Active Directory, but all of them implement a protocol called LDAP, Lightweight Directory Access Protocol. This is basically like having a SQL query language interface for querying directories, but in this case it's its own proprietary little language, but it accomplishes the same kind of thing as SQL does. Any of our directory services, whether you call it an LDAP service or compliance service or Active Directory, are going to do a few things for us called authentication, authorization, and accounting. You don't necessarily have to do all of these, but they should have the functionality there to do things like authenticate a user logging in, to authorize a user in terms of what can those users do once they're on the network, and then keep track of what people did when they were operating on the network in case there's any issues later on. And I left off a slide here that I meant to put in, but if I had put it in here, what I was going to do is just note that there are 3 different contexts that we might be concerned about related to this authentication, authorization, and accounting, and that is you might be managing local resources on a particular computer. You might be concerned with managing a service where all the resources are on a single server, so not on your local device, but on another server. And then a third case would be where there's distributed resources across an entire enterprise, so there, in which case you're accessing lots of different things. All right, now we're going to talk about email. This diagram pretty much sums up what we learned about related to email, that if you are going to be sending an email, then you use SMTP, usually over port 587 from some client software. You send it to a mail exchange server that is close to you. It then uses SMTP to send it through multiple transfer agents, ultimately to another MX mail server, meaning this is the destination, kind of like the mailbox where it's ultimately stored, whereas all the other SMTP servers on the internet just pass it along like a hot potato, but it stays here ready for pickup. And then when you pick it up, you can use POP using secure or unsecured ports, or IMAP. Some of the key differences being that with POP, you remove a message from a server, and with IMAP, you leave it on there. One other thing to note is that in order to send an email from one place to another, you have to look up the domain that's associated with that email address. And so before you send things out across a bunch of SMTP servers, there has to be a lookup to find out what's the IP address associated with a particular email address. And of note, in your DNS configuration settings, if you're configuring that, you can separate the fact that your web address might be on one IP address, but your email might be on a different IP address. That way you can segment things on entirely different service providers if you want. In addition to what I just said, note that you can also send and receive mail by accessing a web browser, in which case, if you're just going on to Gmail, then you're using HTTPS port 443 or port 80 to ultimately send and receive email communication. We also talked about web technologies. At a high level, we learned about web servers and web browsers. Originally, web browsers were just meant to display HTML content as well as images. Now they do more than that. They can include videos, and they run JavaScript and use CSS to format things. But originally, it was just kind of a display application. And web servers, originally what they did is they just looked for HTML documents or maybe another document on their local hard drives on the computer that they were sitting on, and they would send those things over the wire to the device or client that requested it. And the communication related to that was sent over the HTTP protocol. So there's like a special little language. So at this point, as it relates to the OSI model, we're talking about the application level. So applications sending information back and forth using their own little proprietary languages that assume that all the other things below them were functioning correctly, like the cables and the routers and the TCP and everything else got messages back and forth. And so now there's just this language that they can, as if they were in the same room talking back and forth with, even though the web browser and the web server might be in entirely different portions of the world. The HTTP request looks like this. In particular, look at the first line. So if you're a piece of software and you're making an HTTP request to a server, it has a command for what type of request it's making, this / indicates the resource that you're looking for. This means it's like a root of the website that you're looking at, but it could be like a / photos / photo2.html or photo2.jpg. And then there are different standards for communication, HTTP 1 and 2 and 1.0. And you also, when you make a request, tell a lot about yourself, like what's the name of the computer that you're sending from, and what's the web browser that you're using, and what are the types of information that you can receive back. In return, again, in this special language called HTTP, you get a response, the key part being the first line, and the fact that it includes status messages to determine whether or not you're going to be, right after that message, receiving a successful document or a server error message or a message saying that you typed in a URL that's not useful. So from the client side of things, in that HTTP request, you can have different methods such as get, head, post, put, and delete. Most common of these being get and post historically. And when you get a response back from the server, there are some pretty common numbers like 404 not found or 200 success. So depending on the range that it's in, it just means whether it was an information response from the server. In the 300 range, it's a redirect. 400 means that you made a mistake. You typed in some resource, some web page that's not there. 500 probably means that your software on the server crashed. All right, we talked near the end of the class about the cloud, and this kind of reframes a lot of what we've done. In the past, a lot of this infrastructure stuff we had to do on premises in-house, and now we can rent a lot of the technologies that we've talked about in the cloud, but we do need to know how to architect them and arrange them properly for usage. So an important concept related to the cloud is just that rather than acquiring and purchasing hardware and software and things like that outright, you can just pay for what you use. So that's anyway, that's one of the biggest things about it, which is pretty neat. There are 3 types of cloud services that we focused on. First one, software as a service. You just use it, and oftentimes you pay by the user. Be familiar with the pros and the cons associated with each of the 3 types. Platform as a service, this is really giving you more than just a web page to use or an email service to use, but a software platform to program on that in theory could scale as your traffic scales. So if you need something that hosts Ruby on Rails or something, or Python, you can just go out there and rent platform as a service, and they'll have something ready to go with Postgres and Python, and it's ready for you to use. Again, be familiar with the pros and cons of this. Lastly, we have infrastructure as a service. So in this case, you are not just acquiring some nebulous platform that you can put programming code and database stuff on, but you're determining how many servers you want, how much storage space you want. Every single device that you allocate there gets its own IP address, so you're allocating IP addresses and setting up networks and subnets and load balancers to distribute load among devices. So it gives you a tremendous amount of power, but you have to know a little bit more about things and what you're doing. Again, be familiar with the pros and cons of these. High level thing to take away from infrastructure as a service is that you can use it to build out an infrastructure for whatever type of traffic for your application that you expect to receive. Lastly, we talked about security in the class. We talked about symmetric cryptography, this idea that if you create a key and give it to both the sender and the receiver, that you can decrypt that. You just have one key, and as long as it's shared and secret, then your communications should be secure. There's another type of cryptography which is asymmetric, which means that there's two different keys, a public key and a private key. Usually the sender, a web server, keeps its own private key secret, but it'll give the public key out to everybody in the world. Using that public key, web browsers in particular can encrypt messages and send it to the server. The server then is the only one with the private key that can unlock that. So it's kind of neat. Be familiar with the different types of technologies associated with symmetric versus asymmetric encryption and cryptography. We didn't cover this a lot, but also don't know that, especially for storing passwords or validating that something that got sent across the wire hasn't been messed with, you can also hash information. But this is unlike our other type of cryptography. This is one way, meaning that once you encrypt it, there's no way to get it back out to its original message. But generally speaking, by applying something like SHA to a message, anything that you encrypt, if you encrypt another block of text, it's going to come up with a different fingerprint or a different result, maybe 256 character string. It's going to come out with a different sequence for every single thing that you apply the hash to. So it helps you then, if you hash something twice, then if you get the exact same outcome, then you know that whatever it is that you're looking at hasn't been tampered with. All right, and last but not least, talking about web browsing and using secure certificates. One would think that perhaps public or asymmetric cryptography would be enough, but that's not exactly how it works. We actually can use both asymmetric and symmetric cryptography, and even, it's not indicated here, but we can also use hashing to encrypt multiple parts of our communication when trying to send, for example, credit card information securely back and forth from a web browser to a web server. The first step, though, is that a server will send to a web browser its public key, its asymmetric key. The web browser will then create its own symmetric key. So the intention then is that for the web server and the web browser to each have a copy of that. So it uses the public key from the web server to package up the symmetric session key that's only going to be used for maybe a couple of minutes. It encrypts that with the public key, sends it over to the web server. Now both the web browser and the web server have a temporary short-term symmetric key, and they can use that to send information back and forth.